And it's time. Welcome back, everyone. So we're moving into week two, but it was a pretty long weekend. It's been a while since we've talked about statistics. I hope everyone had a restful holiday. You didn't have to work too hard, get caught up on anything. Not too many announcements today, other than we're about to start chapter two, and our first assignment number one is due today. But any questions at the moment before we get a little further into the announcements? Okay, just a couple quick thoughts I wanted to put out there, just because we're still kind of starting out. It's just week two. We're using really chapters one and chapter two as a way of a big vehicle for just getting used to our studio, how that's problem is going to be working in the course. So we used it quite a bit in chapter one towards the last part. We'll be using it again quite a bit more in chapter two as well. And also a big purpose of both chapters one and two is pretty much about the prerequisites for this particular class. There is no statistics class prerequisites whatsoever to this course, which is strange. And so these two chapters serve the purpose of kind of getting everyone on the same page before we go into the next chapter, which will be chapter 11. We'll be moving into the normal distributions, and then pretty quickly after that, into the actual namesake of this course, statistical methods. But that's where we're at so far. And as far as the homeworks go, pretty much I'm going to start grading on Friday. And in the best case, I'll have my grading completed every single Friday. In the worst case, you'll know if I'm behind, if I'm starting to lose a little bit of control of my own schedule, because in the worst case, I might have your homework graded, finalized, and sent back to you on Sunday at the very latest. I try to make sure I never get a backlog of homework grading because that is really stressful for me when things start piling up. So Sunday is my get everything caught up day. So that might be the last day you get your work back. But again, I start grading on Friday. And as far as the due dates go, think of my due dates as fundamentally it's all about pacing. If you're getting your assignments done well ahead of the due date, as many of the class have, I've seen lots of submissions already turned in, then you're always going to be considered fully caught up. But if you hit a busy week, maybe other classes have big projects or exams, maybe life is getting a little bit out of hand, if you get a little bit behind on your assignment, then I don't have a late policy whatsoever in this class. I'll take even the late assignments at full credit. So try to hit the due dates as best you can. There's always going to be a 1 week turnaround, but it's really just for the sake of pacing. And I'm typically going to be grading those assignments on Fridays. I think that's all the announcements I had for today to start us out. Any questions or comments at all, folks, before we begin now in chapter two? Okay, let's get started then. So chapter two, I have two files that are going to go along with it. The assignment has a due date of the 28th, which means my intention is to have it finished today for the 1 week turnaround. If we decide to take just a little bit longer, I'm not going to try to just talk really fast through it and race through it. Sometimes these due dates do get pushed back if we need to finish this when we come back next Monday. So we'll see where we end up. First, chapter two starts off with a gigantic wall of text, but again, with no statistics prerequisite, I felt like we should define the mean at some point, right? There should be a paper trail of what exactly it is and the standard deviation. First, this is just a big roundup of the notation that we've been looking at in chapter one. X is going to be the variable of interest. X usually will have a name like time, number of cells, anything along those lines. N is going to be the size of the sample, the number of observations we've collected into the data set. Then the first, the second, the nth observation are denoted by x sub 1, x sub 2, up to x sub n. X bar will be the mean of the sample. We often just say the sample mean, or if you like to write in a possessive way, samples mean is a great way to think about it. And S will be the sample standard deviation. And we probably have all a great idea of how to compute the mean. The idea is you take all the observations in your data set, x1 through xn, add them together, divide by the sample size n, and you've computed your x bar, the so-called sample mean. Oh, I forgot to load in a highlighter. Give me a moment. This has to be done every time I open this computer. The environment resets each and every time. I'll get better at remembering to load everything in. The formula to the far right is just a compact mathematical way to express the same sum divided by n that you see on the left. The way we'll actually compute these in class is in this way. Let me change the size of that. Using our syntax, we're not going to do these things by hand. That's not the point of this course. We're going to be using technology to do these kinds of computations. All we have to write is mean x, and we're done. Where recall x is just going to be the variable that you possibly defined in R, for example. So take mean x, and you get your x bar. Kind of a nice, fast operation. Likewise, if we're going to calculate the variance, it'll be computed through this formula. We have x1 minus x bar through xn minus x bar. We square all those distances. So notice the mean plays the role here, and in the compact formula, we divide by n minus 1, and now we have the sum of the squared deviations for the mean. Well, the mean itself is going to tell us what the typical value is, the center of the data set. That's what we were trying to do qualitatively in chapter 1, which might have felt uncomfortable to some of us. This is just giving us a numerical value to put down. The variance is doing the same kind of thing, but it has kind of a trouble with the units. If, say, our data is in units of seconds, then so is the mean. We get seconds here when we compute it. But the variance is in units of seconds squared, which might not even make sense in the context. So using that as a motivation, we square root it. This brings the unit back to seconds. And now we're in the more familiar statistic, potentially, the sample standard deviation S. So we just square root the variance through this formula. Or if we're using our syntax, all we're going to compute is SD, standard for S standard deviation. Give it the variable you're working with, X once again, and our work is done there. So those are really 3 statistics defined, but the big ones we'll be using, and another set as well later on in the notes, will be the mean and the standard deviation of the sample. Any questions or comments so far? Okay, so again, possibly stuff we've seen before, but it's good to actually define things rigorously once and for all. For just a couple of related comments, if we have a nice distribution, it's unimodal, roughly symmetric, we think of the sample mean as a great way to describe its center. And unimodal just means there's one main peak in that data set, and the sample standard deviation will describe how spread out it is. This is kind of hard to say how it describes how spread out it is until we go back to something we'll see in chapter 11. The empirical rule, or the 68-95-99.7 rule, tells us if the distribution is nice and mound-shaped, just one main peak, and if it's at least roughly symmetric, if we have good symmetry there, then we can find 95% of all of the observations in the data set, x1 through xn, are within 2 standard deviations of the center, the mean itself. So that's how the sample standard deviation describes the spread, and the mean will describe the center. But notice we've been talking about symmetric distributions for these. The more and more skewed our distributions become, the less and less of a good job both of these 2 statistics will do in describing the center and the spread. So we're going to look at another set of statistics as well on these notes. And again, just to get started, kind of a warm-up for R, here's a really fast problem that has no context whatsoever other than there's units and a negative value with a unit of inches. So this seems like some kind of directed distance kind of problem. So just as a warm-up, let's compute some statistics and see how the syntax above is going to work. But again, that's our major objective in chapter 1 and chapter 2, getting these things defined and practicing with RStudio before we go on to the later statistical methods. If you opened up a clean version of R, it might look like this. So first thing you want to do, like we mentioned last week, is click on this button for new file, click on the very first option, or just hit Control-Shift-N, and we get this script region right here where we're going to import information. This is a very small data set, 5 observations, so it's probably faster to just type this out. So let's call this sample. You could have called this X. I'll use the left arrow to say the sample gets the output of whatever we're about to write next. Lowercase c, to combine all these observations, we'll drop units and just type in 5, 13, -12, 7, and 2. So now our data is imported, hit Control A, Control Enter, and that variable should appear on the right. Now, again, it's a really fast problem, no context whatsoever, really. We're just going to calculate the sample mean and sample standard deviation. And R is meant to handle statistics, large data sets, so it's a fast operation to take. Just type directly mean, X, or not X, mean of whatever you defined your data to be, sample, SD for standard deviation, sample, and this does the job for us. Because I didn't store this into a new variable, it's just going to output the results at the very bottom console down here. So hit Control A, Control Enter. If everything went according to plan, this is what we should see. If something goes wrong, let me know. I'll be happy to help out. And a lot of people took advantage of that on assignment 1. Some strange things can happen to syntax. Say issues defining the variable, missing commas, missing parentheses can cause havoc. If you're following along in class, even if you're in the in-person section, you could say even log into Zoom and just put into chat what your syntax is if you're experiencing any problems, and then we can diagnose it as a class. But so far, so good. Any questions at all, folks, getting those 2 numerical values? Okay, next question we might have is, how do we report this stuff down below? Purpose of example 1 is kind of a warm-up, but also when you're doing the homework in this class, there's lots of ways you can write out your results. So let's say for option 1, if you have a Word file and you just want to write down a quick report of what you're doing on this problem, you can just say, let's get this over here, X bar equals, don't like it capitalized, but I'll try not to be super picky. Wouldn't mind if yours is capitalized. X bar is 3, and S equals, probably looks a little nicer if we put a comma there. S equals, if I don't say anything about rounding, then just use the most sensible approach. Let's go for a 9.3 for this problem. And that'd be a totally fine way to write your results. We're just typing things in directly, and that's completely fine always. If you write out something like X bar, it might look a little bit funny, but everyone in a statistics context would know exactly what you mean. Option 2 is to essentially do the same. This is how I would typically type this out if I was doing it personally. Now, you never have to do this, but some people are pretty curious. The equation editor is being used a lot all over the place in these notes. So if you hold on Microsoft Word on a Windows machine, Alt plus, this is what pops out, the so-called equation editor. And you can type X with a bar. Make sure you put in that specific slash. Hit space once, and a bar appears, and hit it again, and it centers over the thing to the left. We can write X bar equals 3. Likewise, S is nothing special, so S equals 9.3. And this is kind of a nice, cleaner way to write these things out. So if you like that, and if you ever have any questions typing out a symbol, I'll be happy to help out. But the purpose of example 1 is to say, I'm not really picky with how you submit your homework. If you type it out plainly like this, or if you're using the equation editor, it's all the same to me. It's really up to your personal preference. And a lot of people I've taken a look at some homework sets have been doing this on their homework. Option 3 could be use a digital pen, much like how we're going to be actually writing out all of our work on the notes here. On a digital pen, I'm not too worried about color coding or anything, but just for the notes above, the mean was in blue, so we'd write X bar equals 3. S, that's a comma, by the way, S equals 9.3. That's a perfectly fine way to go as well. Then next, option 4. you're welcome to do the following. Handwrite the results on paper. So if you prefer to print out the assignments and just write things down on paper, that's okay as well. I've been putting in spacing to accommodate that if that's the way people prefer to go. If you're writing things on paper, occasionally you do have to include graphics. And if that's the case, be sure to email any graphical displays or submit them to Canvas. So that would be another fine way to go as well. I think that kind of covers just about all bases of how you might write out your results. Again, for the course notes, I'm going to be using the digital pen a lot, but if I was doing this personally, I think option 1 or option 2 is a quick way to get things just written down fast. Well, any questions at all, folks, about just typing in information on homework assignments or getting the results down as well? Okay, so that's a quick problem to get through. And these problems are kind of boring if there's no context. So my favorite kind of problem to bring to a class like this one has context. If there's no context whatsoever, it's just a quick warm-up kind of exercise more than anything else. So here's an interesting related scenario. I believe I got this from our course textbook, but I don't have a citation on this one, so I'm not totally sure if this is real data or not. It might be fictitious data, but still, it's got context, so it gives us a good feel for what a real statistical problem might look like. So starts off by saying a veterinary anatomist investigated the spatial arrangement of nerve cells in the intestine of a pony. So it looks like some serious work they're doing there. Maybe there's something going wrong with this pony medically. The anatomist removed a block of tissue from the intestinal wall. So that's kind of morbid, but that's took a little biopsy, I guess you could say. Cut the block of tissue into many equal sections and counted the number of nerve cells of the 23 randomly selected sections. So maybe there's lab staff, maybe graduate students were assisting with this pretty meticulous work under a microscope. And however, they cut this very, very carefully. When it said 23 randomly selected sections, one thought is that informs us of the sample size. N, oh, that doesn't stay highlighted. There it goes. N is 23 in this problem. The actual data is here, broken into 2 columns just so that it didn't take up too much vertical space. So some of these slides had 35 cells on the higher end, it looks like. Some of the slides were on the lower end, around 12 cells and so on. All we're going to do with this, imagine this is the very first start of a statistical analysis. First thing we want to do is visualize all this data, describe its shape, and then go beyond what we did in chapter 1. We'll describe the center and spread, but we'll put a number to it. We won't say, well, the center is approximately here and the range goes from this to this. We mentioned before that was just a chapter 1 approach because we just hadn't gotten to those statistics just yet. So first job, let's get the histogram, then we'll compute the statistics. Well, any questions so far, folks, with the context on this one? Okay, this is where you probably want to have this file and this file ready to go, say downloaded somewhere onto your machine on a thumb drive, something like that. I have mine duplicated here on a thumb drive, but I'm not actually going to directly open it. We want to make RStudio open these. We could work just like we did on example 1 and meticulously type these in one after another. But I guarantee you, if I have to type in 23 observations, there's a significant chance I'm going to make a mistake. So let's just make RStudio import this for the sake of accuracy. We're done with all this. I'm just going to hit delete. Let's not hit delete here. Sorry, one thing I forgot that I need to remind myself is I'm trying to leave a paper trail every time we use RStudio directly on the course notes so that if you ever need to go back to this information, you have a way to check what did we do in class as well. So let me put that in. If you ever notice any of this R syntax is missing, we'll always put it in a box. Let me know and I'll get it corrected right away. Okay, so let's get back to example 2. Sorry for the distraction there. In example 2, let's first wipe out the syntax. We're done with it. We've saved it on the notes. We want to wipe out what's stored just in case a conflict could occur. So this is just a best practice. Click on the broom icon there. Click yes, and now the environment is reset. Now here's the massive quality of life improvement with using RStudio specifically. Importing this data set is pretty fast, actually. We saw how it went in chapter 1, so just as a refresher, let's go a little slow again this time. Click on this region here where it looks like an Excel sheet. Click import data set. The very first option is what you would want to go. I'm always going to give you nice, easily read files. That works on option 1. Now go to wherever you've downloaded this. I need to go to my thumb drive. Double click on example 2. And this window is automatically set up exactly the way we want it. I don't need to change any of the options here. You can tell it's on the right track because the variable number of nerve cells is bold, not the numerical data. That's in just normal text. Click import, then it visualizes our data for us. So it should be essentially the same that we see right here, just one column. And these start popping up a lot every time you import. They're good as a double check the data looks the way you want it to look, that it was imported correctly, but I often just click it away after it's imported. This is where I usually look to the right. Often I hit that play button to see what's stored in the data frame, example 2, just one variable, number of nerve cells. So we're ready to give a histogram. We can type this on one line just right here if we prefer. Go hist. Let me make this a little bit bigger so we can see how the graphics emerge. So histogram, type in example 2, but you don't have to type in a lot. It's a good idea to type slowly because we need to type that in perfectly, especially if it had some really long name. Type in example 2, exactly as it's shown. Using autocomplete's a good idea. Hit the $sign. And again, it's good to take advantage of the RStudio IDE because typing this in verbatim sometimes is a challenge. So just click on it. And now no worries of accidentally putting in a space or not pluralizing cells. Anything like that isn't going to import this data. So just to make sure we're on the right track, let's run this right here. Hit Control A, Control Enter, and there's our histogram. We mentioned last class that there's a couple things we have to clean up. So what we need to fix on this is that's not correct. We would never want to publish any graphics that says something like that. So imagine this is going into a journal when you submit a homework assignment. We should have something more descriptive there. And same kind of problem. We don't want any artifacts for the actual code in R that appear in our graphics. This should just be a nice clean title, or just totally delete it if you prefer. I'm going to always leave that your option. And a better description here using the units. So let's fix both of those issues at once. But first, at the moment, any questions just producing the histogram so far? Okay, I have pretty limited horizontal space going this way. So when I type comma, I'm not going to put in more information because it's good to just see everything at once, not having to worry with the vertical scroll bar. So after the comma, just hit enter and start typing in more information. I mentioned that I often go like this, main equals nothing between quotes. So I always delete the horizontal title or the main title in the histogram. But that's just a personal opinion that I don't find it necessary. You might have a different opinion. So if you wanted the main title, you might say something like this: nerve cells in the intestinal wall, running out of space, so let me hit enter there, of a pony. Or anything that just seems as interesting and appropriate. I'm not going to be too picky on what you put in on the main title, other than make sure to clean up this or just delete the whole title outright. Your choice on that. So make sure you do a comma right after the quotes. Let's fix this as well. The syntax is xlabel or xlab is what we would type in. Another set of quotes, and let's just say number of nerve cells. So that's the unit. We don't have to say anything beyond that. Hit Control A, Control Enter, and this is our more cleaned up graphic. Now, if we were writing this out as a homework assignment, just like before, you have a lot of options to do this. If you're downloaded this and you're working in Microsoft Word, you can just screenshot this, import it directly into the assignment. If you're working by hand on paper, then you can just take this, put it in, say, a new document, send it to my email, upload it to Canvas, anything like that would be just fine. If you're coming to class in person, you can just have this printed out as a separate thing to go along with your hard copy. So I'm going to use a quick method, Windows Shift S, to just do a quick screen grab. Since this looks like about the right dimensions to emphasize what's going on with the data, let's drop it in. And it's not perfect. It got kind of cut off onto the right. So for me personally, that would really bug me, but I'm not ever going to be that super picky on anyone's assignment. But let's fix that. It is a little bit cut off there. The 0 is not quite right. So second try. If you're not using the Windows Shift S approach, the clipping tool, other approach is to hit Export, copy to clipboard. You get a new window that you can resize. And if you have to resize, this is a good operation as well. I think it was about right the way it was. I saw in this particular version an install, and I needed to click on Metafile last week, then click Copy Plot, drop back into the document, hit Control V to paste it in, and that's a much cleaner screen grab than the prior one. I think the resolution might be better as well compared to the other one. It had kind of a fuzzy look to my eyes. Well, we've got it, folks. There's our distribution with the numerical value shown, but now as a display, we see a little bit more structure so far. That count of 12 seemed really unusual to me. I might have thought of it as an outlier, not really matching the pattern of the data, but it's not that far off. It's connected with the data. So now that I see what the display really looks like, I have a different opinion of what's going on with these data values. So we've displayed the data with the histogram. Now we want to describe its shape. So that's our next step. Well, any volunteers for what you would say for this display? What would you say about the shape? Would you consider this to be skewed or symmetric? Yeah, I agree with you. It does kind of look symmetric to a degree, but as far as symmetry goes, we usually want to look at where the main peak actually lands on this data. Most of the data is aggregating between 25 cells per slide and 30 cells. So this is the main peak. Just a reminder, anything that we write in orange is just meant to be a comment to go along with the lecture notes, not something you would have to say on each and every assignment. So we have a main peak there, which means there's one main peak. The data is unimodal. And if that's where the data centers, it is trailing off a little bit more to the left, well, a good bit more than it is to the right. So I agree with your assessment. We can say that the distribution of nerve cells is skewed to the left. We'll keep going on that comment, but left skew, once again, is the way it's trailing off in this direction here. If this wasn't here, then I would be more likely to say roughly symmetric. It still would have a kind of a left skew sort of look towards it, but this really kind of makes that picture look like definitely more data to the left than to the right in the way it trails off. Next thing we want is to describe the center and the spread numerically. But we're not doing anything too fancy compared to what we did in example one. It is not horribly skewed. We're going to see worse data than this. So we can use our statistics, say, X bar and S. So let's calculate those values and see how they come out. But pretty fast, we saw how it went. Already, for our example one problem, notice that my graphics display, my graphical display just kind of dies if I make this window too small. So if you ever see that, you just have to resize your RStudio environment. That'll happen a lot in class because we have a tight resolution to work with here. But now we're getting some quick summary statistics. We can say mean X, excuse me, not X. R is going to have no clue what X is. We would have to cite this once again, number of nerve cells. So let's call this example 2, $ select, number of nerve cells. Then SD for standard deviation, call this example 2. Same way, hit the $, select number of nerve cells, and this should output the statistics that we're expecting. So let's run this, see what we get. Hit Control A, Control Enter, and those are our values down below here on the console. I think what's sensible for these data, this was integer values, so let's round these to 1 decimal place. Seems about right in this context. So use your best instincts on rounding if no information is given, like on these problems so far. I'm not going to be too picky on how you round. So let's make this 26.6 cells. For the center, notice that's right about here. This is where X bar is. That looks about right. It's where the main peak of the data is in the very first place. And then next, standard deviation rounded to 1 decimal place is 7.1 cells. So that 7.1 describes how spread out the data is. And we can do one last check here. If we take 26.6, add 2 standard deviations, that's going to be 2 times 7.1, we get a value of 40.8. So that's right here at the limit. So up to this value, this is going to be X bar plus 2 times S. So if we go in the opposite direction, take away 2 standard deviations from the mean, that's going to be hit up arrow, move left and just put in a minus in between. We'll get a value of 12.4, so we're about here. This is X bar minus 2 times S. And our description for what the standard deviation was supposed to do through the so-called empirical rule is 95% of the observations approximately, if we're at least roughly symmetric and bell-shaped in the distribution, should be within 2 standard deviations of the mean. And yeah, that looks approximately 95%, probably closer to 100% on these data. And so the empirical rule does check out. This standard deviation is describing how spread out the data is in that way. Well, we got it, folks. This was just a quick problem to see how to look into a display of data, the histogram, and relate it to the center and the spread using these 2 statistics. Any questions or comments at the moment?
Are you going to put the everything you typed up in RStudio?
Oh yeah, thanks for reminding me on that. Yeah, that's my intention. Each time we finish a problem, I always want to leave a paper trail, so this is what it's going to look like. Let me hit Control C. And it's always going to be at the very end of the problem in a box. Thanks you for the reminder on that. If you ever notice I'm about to forget, dive into the next problem, it is never ever rude to interject and say, hey, Mike, can you leave the R syntax? And I'll be happy to help out. And the homework exercises are pretty parallel to what we're doing in class as well. So this is meant to be a help. If you're doing something slightly different, you might have exercise 2, a different variable here, change the information as needed, and that'll be the experience for using RStudio. It's not meant to be a coding class. So we're trying to share as much as possible to give everyone else a help. One slight word of warning, it's a really bad idea to type syntax inside Microsoft Word. Let me show you what can go wrong, which is kind of maddening. It took me a while to figure this out. You see those quotes right up there? They're actually really, really specific. They paste incorrectly. So if I paste this syntax out back into RStudio, I won't run into any problems. But if I were to type a quote inside Microsoft Word itself, that symbol right there is not the same as this symbol, and RStudio is going to hit a syntax error just immediately. Those are the wrong quotes. And I don't know how many small issues like that could ever come up. This is possibly not the only issue. So best practice is open up a script or maybe open up just a text document or Notepad++, anything like that to do all of your syntax writing. I'll almost exclusively always do it right up here inside RStudio itself. Other questions so far? Okay, so these data, certainly they were skewed to the left, but they weren't terribly pathologically skewed. So the empirical rule of most of the data being between two standard deviations of the center of the mean did check out for this particular problem. But the more and more skewed these data become, the bigger and bigger problems we're going to run into. So that's what the next example is all about. How bad can skew get? There's no limit. It can get more and more skewed the more extreme you make the data. The more you start making things shift further and further to the right, the bigger problem the statistics that we were just working are going to have. The empirical rule will fail on these kinds of data. And just to get a feel for what's going on with these data, let's read through it, go through it slowly, and see just what's going on. So it says this is the 2015 Urban Mobility Scorecard from Texas A&M. Included the data on the estimated cost in millions of dollars resulting from traffic congestion for different urban areas in 2017. So that's probably a big report saying exactly how they define traffic congestion and how we estimated a loss in millions of dollars caused by traffic congestion. That seems like a pretty big problem on its own. They did the best they can at this university, and here's the result. The following data is not a random sample. This is for the 13 largest US urban areas that had a population of over 3 million. So they're estimating, for example, in 2017, New York lost $15 million strictly due to traffic congestion, approximately, by this particular study. We have other cities here, San Francisco, Houston, Atlanta at the very bottom. All of these are pretty big values, and this is just the 13 largest. If we put all this data to a histogram, like we've been doing in the last problem, here's what we would get this time. And this time the skew is pretty substantial. We might say something strong along the lines of the data are, you could say, severely skewed to the right, substantially right skewed. If you just said right skewed, I'm okay with that as well. But sometimes it's a good idea to just convey how bad is the skew in your mind when you see a display like this. I personally say something along the lines of the data are very strongly skewed to the right. So kind of a rough data set we're looking at. And this has some problems. Our statistical methods for a small sample size, 13 observations, is not going to work well for these particular kinds of data, not our default methods. We have to know when data like this comes up, what are the new methods that we have to take? And that's the purpose of looking into histograms so much for quantitative data in this course. It says, explain why the sample mean should not be used to describe the center of the data. So here's the trouble with the sample mean. We are skewed to the right, then the mean, X bar, is pulled let me fix the wording here. To the right for these data. The sample mean follows the direction of the skew. And like we said, there's no limit to how skewed the data is. If I took the observation that's here, this is New York City, and just moved it further and further to the right, the mean is going to budge and follow it at the same time. If I had to guess where the sample mean is without doing computation, I would probably guess it's close to somewhere around 4, maybe slightly below, slightly above. I'm going to put it slightly above. We can compute it if we like. I'll let that be up to the class. This is where I would guess X bar is likely to land. So why is it pulled to the right? The trouble with X bar is, if you imagine this as a real physical system that you're going to build, maybe you went to Home Depot or Lowe's and you bought a big long board. Then you brought maybe gardening bricks and you stacked them to this height here, and proportionally these particular heights as well along that board. X bar is going to be the fulcrum, the balancing point. These values on the right skew have tremendous leverage. And so to get the whole system to balance, X bar has to be pulled to the right. That's not exactly where we would consider the true center to be. We put these data in example 1. The center, I think a lot of people would say, is somewhere right around here, maybe around 3, or maybe slightly above 3. So the center, the more typical value, is here. X bar didn't measure it well, so we need a new statistic to make that measurement. That new statistic we'll define on the next page of the notes will be the sample's median, which is nothing but the 50th percentile of the data. The 50th percentile surely measures the center because, by definition, the 50th percentile puts half the observations to the left of it and half the observations to the right. It is not as affected by skew, but that's the problem with the mean for these particular data. Well, any questions so far, folks, with issues on part B for skew? Okay. It gets worse because if we have a problem with X bar not measuring the mean in the way we'd like, having a bias in the direction of the skew, the standard deviation is even worse. If you attempted to redo the empirical rule on these data, it's going to fail spectacularly. 95% of the data will not be contained between these two measurements. In other words, this is not going to work out whatsoever because our data are not at least roughly symmetric. We have very strong substantial skew this time. And in the very first place, the standard deviation is defined in terms of the variance, which is defined in terms of a central value X bar. So if X bar is off, the variance is not a good computation, and square rooting it, getting back to the standard deviation, won't help as well. So if one statistic is not conveying the center well, the dual statistic, standard deviation, won't work either. So what should we say on the report? We don't have to say all of that. That took a lot of oxygen to say, but we can say very briefly, since X bar does not measure the center accurately, the sample standard deviation S, I'll just say S, the way it was worded in the notes as well, will not measure the spread accurately either. And if you want to be more specific, let's put this in orange. The 68, 95, 99.7 rule will fail for these data. The skew is just simply too strong for this rule to be accurate for us. Well, that's a rough set of data. Again, if this was a random sample, maybe a different context, and we had to analyze these data, we're going to need to work a little bit harder than the standard methods that we'll see in chapters 17 and so on. They'll be the non-parametric methods that we'll look at towards the end of the course as time permits. So we need to find a better way to measure where the center is because X bar is not doing a great job. And we need to find a better way to measure the spread because S has a problem as well. And that takes us to the other two statistics down below. So here's our fix. If the data is strongly skewed, like in the graph we saw there, we're going to convert over to using the sample's median. I have the full definition here, but once again, we're going to use R to calculate this. The median is the 50th percentile, like we mentioned before. The way we compute it, if we really want to do it by hand, but you never have to do it in this course, is first you order the observations from smallest to largest, or largest to smallest, that'll work too, but this seems like the sensible way to do it. Then the value in the middle, if you have an odd set of data, is your median. Averaging the two middle values will give your median if the data is even. So this is doing it by hand, but it turns out the median value M does not have a unique way to compute it. RStudio has its own version that it implements, but either way it's computed, either by hand, using this route, calculator, or RStudio, it's always going to do this, be the approximate 50th percentile of the data set. So that's the big takeaway for the median value M. And the way we compute it is we just type in median X, much like you might have typed mean X, and it computes it for us through R. Let me write just a note. This is R syntax, just to be specific. So that's how we'll compute the center. To get the spread, we'll look into a lower quartile called Q1. This is the 25th percentile. We'll look into an upper quartile called Q3. That'll be the 75th percentile. And then we'll just compute the difference between those quartiles. How far do you have to go between quartile 1 and quartile 3 will be called the interquartile range. So this takes the place of the sample standard deviation, lowercase s. It gives us a spread, and what it does specifically is it tells us the spread or the distance or the range of the central 50% of the observations in the data set. We have to compute it in R. We'll just say to R, do IQR, all uppercase, X. And that will give us the interquartile range. So those are our two brand new statistics. It's weird to have quartile 1, quartile 3. You might wonder what's quartile 2. That's the median itself. It's just usually called the median rather than quartile 2. And we can put even more statistics on the paper. We want to describe the extent of a data set. We can go from the minimum to the maximum, say where the 25th percentile is, quartile 1, the 50th percentile, the median, the third quartile, which is the 70th percentile. And this gives us a great way to just visualize a data set. So that's what we'll do on the very fast contextless problem on example 4. Any questions at the moment, folks? Working through thinking about these new definitions here. Okay, like we mentioned, in this course, we are not going to compute any of these values by hand. We'll be taking advantage of the RStudio calculator to do our work for us. So example 4 is just a warm-up. Let's give this a try. So first, let's clean out this environment. Here, I'll just hit Control A and delete to wipe it out. Let's import the data. I'll call it sample again. Sample gets the output of lowercase c to combine 113, 124, 126, 128, 131, 133, 135. Let me double check that. It gets a little sketchy putting in multiple observations. Okay, I think we've got the data in. Hit Control A, Control Enter just to make sure it imports right. And by the way, if the graphics are kind of a distraction because that's not the problem we're on, You can just click on this icon as well to clear it off the environment, but that's completely up to you. Sometimes I'll just forget to do that. It wants the 5-number summary, so we need to calculate min, quartiles, and median. We know how to do the median, we just calculate that value. And then the maximum. So that seems like a chore, but this is not too bad. If you want this 5-number summary, this is implemented into R as well. Just type summary, given site summary, sample, and it gives us exactly what we would like. Hit Control A, Control Enter, and here's our 5-number summary. It even gives us a nice formatted table, so that's kind of helpful as well. If you get a nice table here, it might feel like a chore to say minimum equals 113, quartile 1 equals 125. No harm in writing that out. But another option is no harm in just copying and pasting down into the document. I'd be all right with that. Make sure it formats well. Sometimes things can break in unusual ways, so I have to be able to tell which is which. It's kind of hard to tell, but if I read it left to right in order and just think these go with these, this goes with this, that goes with that, I would say that's readable, but it looks kind of hard to read. I'd have to really stare at this hard. If you wanted a better way to import this result, you could use the quick screen grab method. Hit Windows Shift S. Only import the part of the console that's relative to the question, but that's from here to here. This table looks a little bit better, so this is a good way to go. So if you import results like this into your document, that would always be just fine. That's a good time-saving strategy. So there's our 5-number summary. We know now the minimum all the way to the maximum, as well as the percentiles in between. Any questions at all, folks, getting those values out? Okay, well, the 5-number summary is so useful that it gets conveyed in lots of different ways, as the so-called box plot is asked for in the next part. Instead of doing the 5-number summary, we can just display the 5-number summary, and that's what the box plot is going to do next. So back to R. If we want some quick graphics based off that, hit box plot. That's option 2 if you just only type in box. Give it sample. Run the entire syntax and error in plot, dot new, parentheses, figure margins too large. That's a pretty weird error, right? But I'm glad it came up because if you ever see this one, it's kind of vague on what R is really trying to say. What it's saying is, I didn't give it enough space to show the plot. This window is too small. So let's bump this up, run it again and see what happens. Hit Control A, Control Enter, and that's the display that we want to see. Here's our box plot. The box plot really shines if we had a categorical variable that splits the quantitative variable across different categories. So if we had something like that going on, we can make really fast side-by-side comparisons. But the box plot is still a useful tool just on its own, even for just one quantitative variable and no categorical variables mixed in. Here, this is the display. And notice the horizontal axis has became a vertical axis this time. If we did a histogram, that would have become a horizontal axis instead. So if there were units, we would have to describe it here. Here's what we would pass to the box plot function. We would say ylabel, the shorthand is ylab. Don't know why it didn't autocomplete there. Let's hope it works. Ylabel equals sample. I don't have any units, so I'll just describe it that way. And there's our really fast box plot. Let's throw this into the graph, take a look at what we're reading here when we see it. So there's lots of stuff going on in this box plot. There's different lines. There's these weird half bars that extend in one direction and in another direction. And then there's this open dot at the very, very bottom as well. Any guesses on what that open dot might be conveying? Yeah, absolutely, Bella. Good eye. This one is an outlier. Well, how do we know it's an outlier? We have a rule of thumb. There's various rules of thumbs, but in an introductory statistics class, more likely than not, this is the rule of thumb that you'd be thinking. It's a rule of thumb in the sense that this is not the end all be all about this as being an outlier. It's just a place to start. Start looking into which observations seem just a little bit off. When I looked at the data, and even when I typed it in, that 113 didn't seem odd to me, but it really is odd. Look how far away it is on this scale. Here's 113. It's completely far away from the main grouping of data way out here. So the box plot is a pretty cool function in the sense that it runs this rule of thumb just right away for us to check for suspected outliers by this particular rule. What it does is it computes the interquartile range. It looks at the difference between the 75th percentile, quartile 3, minus the 25th percentile, quartile 1, and anything that is more than 1.5 times that interquartile range, which is that distance here, away from quartile 1 or quartile 3, is flagged as an outlier. So let's put in just some quick information for what we see here. This value corresponds to the maximum value in the data set. The maximum looks like it was 135. I mean, we definitely see that. So that lines up. This value down here is the minimum, but it's also a suspected outlier by the rule of thumb. Then we have other interesting things going on. It's a box plot, so it's natural to see a box. This heavy line seems to be emphasized more than the others. This is the medium M. Let's double check that. It says the median should be right between 125, 130. We report a median of a 128, so that looks about right based off the box plot. So in a certain sense, the box plot is just conveying the 5-number summary in that way. Likewise, if we look at first quartile and third quartile, they're right here on the box plot. The height of this, moving off to the left, just above, or it looks like exactly 125, is quartile 1. Sorry for all the arrows, it's getting kind of busy. The height of this one, quartile 3, should be at about 132. That looks about right. And then last thought is this distance here is the IQR, the interquartile range, is this distance, or the length of that particular line segment. So that's why this one was flagged as a suspected outlier by the rule of thumb. It's more than 1.5 times that length away from quartile 1, the lower quartile. Well, that's a lot of statistics displays so far. Let me recall to post this. But it didn't take a whole lot to compute any of these values. This is the entire summary of the R syntax. We'll put it on the next page here. So far, we've looked into our main statistics as it relates to quantitative data. Any questions or comments at the moment getting through these problems so far?
Would that smaller line beneath the plot, would that be the recommended minimum if you have almost outliers?
Yeah, that's exactly what it is. Thanks for mentioning that. So this line, sometimes this is called a whisker, and sometimes this is called a box and whisker plot. This one is the maximum. But like you mentioned, if there's an outlier, this is no longer the true minimum, but it is after deleting the outlier, just exactly as you said. Let's put that in as a quick note. So just one more arrow. The height of that line segment down below here is the minimum after removing all outliers flagged or identified. Let me try again on that spelling. by the rule of thumb. Referring to the 1.5 IQR rule of thumb below. Other questions so far? Okay, well, we have our, don't know why I have a equality sign here. Let me undo that. That seems like a sentence without a period or a final thought. We have all of our major tools so far, but the other big takeaway here is, why do we want to use the median and interquartile range? The big thought is M and IQR are highly robust against skew and outliers. Robust meaning, if I took an observation like the 135 and made it bigger and bigger and bigger, bumping up this skew to higher and higher values, well, moving one value like that isn't going to affect the median and interquartile range too much, if any at all. Let's check that out in RStudio. Let's put in some zeros here. If that's a 1350, it's now a gigantic outlier. The skew is now obscene because of that one outlier in the data set. Let's take a look into the new values we're going to get. Hit Control A, Control Enter, and notice, oh, hang on, let me go back. Notice that our median is still 128. First quartile is still 125. Third quartile is still 132. Eventually, if I keep doing this to all of the data, say if I bump that one up to times 10, I'm going to see these values change. And I'm also going to get an error. There we go. But I have to affect a whole bunch of the data to make that happen. Looks like first quartile is unaffected after bumping up to two gigantic outliers in a small data set. Median is the same. The third quartile is starting to blow up. So it's not immune to skewness and outliers. It's just robust, much more robust than the original statistics, the sample mean and the sample standard deviation S. So when we have highly skewed data, these are our next go-to methods. Well, what we'll do next with our remaining time is look into a problem that actually has context to see how this all comes together. And that's going to be our example 5. Actually, you all looked into a pretty closely related data set on the first homework assignment, where you had a variable very similar to this one, recruitment, and you had a time variable as well. We had to produce a histogram of these data, which is pretty strange because there's two variables. You have to decide, did we mean a histogram of the year variable? Well, that'd be a really boring histogram. It would just be one rectangle per year, completely flat and uniform. Doesn't really tell us anything. But in the homework assignment, what you really wanted was a histogram of the data values that go along with the time component. There's certainly more to this data. You might have wanted to produce a time plot. You might do that on these notes if you're curious, but you didn't have to on homework assignment number 1. So what's going on with this problem? First, let me see if I can fix the grammar there. We're told recruitment in this context refers to the addition of new members to a fish population. This is a very important value, is an important measure of health of the ocean ecosystems, health of that species of fish in particular. And so we have data on recruitment of one particular fish, the rock sole in the Bering Sea. Data measurements are from 1973 up to the year 2000. So that's the year component. And this is how many millions of fish was added to that population. It's kind of interesting, in 1973, it was at a really low value. We might imagine, but we'd have to look into this a little bit further, maybe this fish was overfished for a while before 1973, and maybe some government forces, some foreign policy addressed this, some better fishing practices. The population started to recover, rebound. It got up to, say, 4,700, and then it looks like it crashed again, and we're not quite sure why, unless we investigate this more and more as well. But as a first look into what's going on with this population, without doing a whole bunch of independent research, first thing we'll do is take a look at the box plot for this particular data. Well, before we delve into the syntax and work on that, any questions or comments at the moment? Okay, let's give this a try. Back into RStudio, expand this out. Let's wipe this out. Hit the broom icon to clear that out as well. And this one is example 5 from the Canvas page. So let's import that to start. Click on this button, very first option, and then we're just hunting wherever this is. Okay, we've got 2 variables. They're in bold, year, recruitment, and millions. So let's import that together. Looks like the same table, so I'll click that off. And we're ready to start. Hit play here to just display the variables. And if we're not doing anything with year, the $ recruitment in millions is sometimes kind of a nuisance in a certain sense. We just dealt with it in the prior problems. Say, for example, when we were on example 2, our syntax looked like this. We just $signed number of nerve cells every time we had to access that one column in the data frame. So every single time. But there's other approaches to doing this. Here's another way to do it for these kind of data. If all we're doing is looking into the recruitment, that's kind of strange. Ignoring the time variable seems like we're ignoring a huge dimension of these data. But for the moment, we're going to look into this variable. Decent strategy, as far as RStudio goes, is let's just extract that variable right here by the red dot, right out of the data frame, so all of our syntax is just a little bit cleaner to work with. I'll call it REC, short for recruitment, gets, latent, type out the data frame, exactly as displayed, so autocomplete's a help. Hit $, go down to recruitment millions, hit enter. Now, if you run this, hit Control-A, Control-Enter, here's the actual data we're going to be using right here. So now we don't have to access the data frame each and every time. In part A, it said, display these data constructing a box plot. So let's go box plot, recruitment. That's not everything we want to say, but let's just see what it looks like running this. Here's our box plot. Probably we want to fix some things here just by resizing this to see if it can make the scale look a little bit nicer. That's not too bad. To me, it's weird to not have an upper capped value here, but I'm going to leave that up to you. I'm not going to be hyper picky on every single problem. But one thing we need on all of our displays is units. If we have an axis with numbers on it, we need to say what that is. But it's just going to be the variable recruitment in millions. You could say for the Roxol and the Bering Sea, but you can also make this kind of terse. I mean, the context is right here. You don't have to mention every single element of the problem. So if we're going to write down the vertical unit very briefly, we'd write ylab equals, hit the quotes to wrap it around since we're passing a string to this, and recruitment in millions. Now, if we hit Control-A, Control-Enter to run, we have some more cleaned up graphics here. It does show the outlier. This was at the 4,700 where the population was at the peak. And if we put this on the report, we've got it. Here's a display of the data. We could have done a histogram, but we're practicing box plot on this, so we specifically went for the box plot. Histogram might have been informative, so if you gave me extra graphics just because you were curious about it, no harm done. So you don't have to do verbatim exactly what's said here. This is just a minimum output that I'd be looking for on a real homework assignment. Now we want to say what we see here on this display, mentioning at least 3 items and focusing on the context. Maybe the very first thing I would mention right away, if I was looking into this problem, if this problem was near and dear to me, I was very interested in this population of fish in the Bering Sea, then I'd be very interested in that value. An outlier is printed. Let me make that slightly bigger. So the very first thing I would say, commenting on the display, is there is one suspected outlier How do we know it's an outlier? Well, R itself used the 1.5 IQR rule of thumb, so I'll just cite that method. By the 1.5 interquartile range, IQR, rule of thumb of, now if you're only looking in the display, you can give me an approximate value, but it's kind of nice to say exactly what it was. It was 4,700. In the data table above, let me scroll to a better spot. 4,700 million fish in 1987. Well, I mentioned one item, but that's a pretty good go-to. Outlier is something that we'd want to discuss and assess right away. You don't have to say suspected outlier, but I do that really for two main reasons. One reason is this was through a rule of thumb, so we want to take another quick look at it. And also, there could just be a bona fide problem in the data. Potentially, if we could take a look at how they got these values, maybe the way they classified the fish was wrong. Maybe other species were rolled into this. There could be some problems in the data, and the outlier is just an artifact of that, something that has to be corrected. Until we really look closely at the data to see just what's going on, it's often just identified as being a suspected outlier, saying we now have more work to do if it's our problem, our data we have access to. But there's two other things we'd want to say. Any volunteers for another great thing to say about these data? Yeah, that's a great way to go. This is another, huge element about the box plot itself is it shows you a central value, right? So that would be a great quick item to check off the list as well. And we can compute it exactly using RStudio, but that's what we're going to do on part D. So I'll just go with approximate, as you were saying. If we're just commenting on what we see on the display, and we take that verbatim, it's fine to just say the median is just below 1,000 million fish. The median is just below 1,000 in millions of fish, or I'll just say million fish for short. Probably a faster way we could say that. I'll just keep it parallel, mentioning it the same way I said it in the first sentence. Well, another interesting thing you might want to say is, you could say a lot of things. You could estimate the interquartile range. You could tell me what the minimum is and the maximum after removing the suspected outlier. But another thing that really pops out at me is skew. These data are absolutely skewed. Recall that the medium M is the 50th percentile. It cut the data set in half. And that tells us if it's the 50th percentile, that from here to here, that's 50% of observations. And likewise, from here all the way out to here is the other upper 50% of observations. We're used to seeing skew on a histogram, but a box plot can reveal it just as well. It's way spread out above the medium M. And it's kind of tricky because we're used to seeing this on a horizontal scale. Does this look like skew to the right, or does this look like skew to the left? Anyone see what the direction should be for skew on this? I just noticed the clock. We're kind of short on time. Sorry about that. This is kind of a fun problem. I think I just lost my time management on this one. Well, it turns out this one would be skewed towards the right, only because it's more spread out in this direction, and this is going to higher and higher values. So for that reason, we would say, moreover, the observations are skewed to the right. And that informs us on what statistics we would actually want to calculate. But sorry for running a minute over on this problem. We're gonna have to return to this one back when we come on Wednesday, or excuse me, Monday's class next week. And then we'll start delving into chapter 11 as well, looking into the normal distributions. But any last questions or comments at all, folks, before we call it a day today? Okay, well, have a great afternoon, everyone. Sorry again for running over. I guess time management gets a little bit rusty, especially in a fun problem like this one. I'll try to do a better job next time, but have a great afternoon. Oh, and I'll be sure to put in the syntax as well. Nearly forgot that one.